So we continue with this morning session with John Barton from Stony Brook, the Donaldson Universal Compactification people project.
Thank you very much.
So is the microphone on?
Thank you. First off, great. So thank you very much for the organizing today. Because of talk. So let's begin with some introduction from classical enumerative geometry. We'll illustrate some of the themes that we'll have to deal with. So let's recall Macy's theorem. So if I have f(x) degree d1 polynomial g of x comma y degree d2 polynomial, or at least define same curves of degree d1 and d2, I can ask for their number of intersection points. And the theorems of this is always equal to product d1 times d2, provided we count intersections correctly. So provided count one with multiplicity and two adding. So these two intersection points are transverse. They have multiplicity 1. This intersection point here, if this is a parabola, two smooth curves leading to order 2, have multiplicity 2. So that illustrates this first issue. Issue number 2, we know two lines always intersect in one point, except if they're parallel, but in that case, they also intersect in one point. That point is just happy. Meaning in compactification. Okay. So in this situation, generically, you don't have to care about lines. So for generic curve with degree 1 and 2, all the intersections will be transverse, 1, and there won't be any. But when we're doing more complicated enumeration sections, this is not the case. There will be issues with non-compactness and issues with non-compactification. And so those sort of become okay. So what I want to do in the talk is discuss enumeration of curves. So there are some classical geometry enumerative geometry results like every cubic surface. Three has a jet on the setup. But the modern theory of enumerative geometry seeks to have the theory of enumerating curves in any graph, which is more common. So let's talk about enumerating curves. So we'll fix vector right x, and we look at the space M of moving curves. Now, this space, well, one way to think about it, at least intuitively, is it's like the intersection of two curves in the plane, or more generally, it's like the intersection of two smooth separations. or has had to be described locally in that form. So definition theory of a given smooth curve. X is described as the homology of C with coefficients in with coefficients in its compacts. One X in degree 0. This part accounts for variations in the map from C to X, and this part accounts for variations in the complex structure of C itself. And one thing you notice is that since C is a curve, this complex, this homology is supported in degree 0. There's no higher homology. That's key to the final complex. So that's sort of algebraic description. You can also think of this space in a more differential geometric style. So this is also described by nonlinear elliptic PDE, and this gives rise to local coordination charts, and described locally as a zero set of some. Well, I guess in this case everything is analytic, so I think I can say F is an analytic function from Cn. So the zero set of an analytic function is, like I was saying before, it's the intersection of two smooth subdirections inside of the graph. So that's what and is local. And just to complete the description here, I'll say the index or the formal mention of M. Well, in this case, it's n minus first term pass X carried C plus n minus 3 times total effect. And 3 to the number 3 coming up. And that's the same 3 as in the title of the model. Convenience. And this 3, this term drops out, and the state of the curves in a given homology class has dimension depending on how much class model. So that's how we'll understand the structure and pieces of practice. So this definition theory discussion, this essentially resolves issue 1. It tells you how to count the one. But there are many ways to resolve it. Many ways of compactifying space. And it leads to quite different choices. So Gromov Witten invariants come from compactification table maps. So you look at nodal curve equals to the map X with the property that the number of has finite number of morphisms of C, which means more from C over X. So when we have a smooth curve X, well, how can we describe a curve? So there are two ways. You can either describe it as abstract curve of the map to X, or we can describe it as Calabi Yau equation. So for the Gromov compactification, we think of the curve as really given by some abstract domain curve. Now, a smooth curve can be generated. Smooth curve, maybe it's a curve on this. So in order to have a compact module space, we need to include domains of some sort. And it turns out that if you're describing a curve of maps, all you need is nodes. That's simple. That's you can get a nice compact module space. Yes, there can be components which are not effective too. They just can't be bottled with one or two. Yeah, so this space is a space. This space is already space because of the automorphism. It's not really a space, it's a market stack or overfold. And because of that, they're all invariants are rational numbers. They're not, in general, integers. Now, there's this proposal from our backup that there's good exists an alternative way of compactifying where you get integer invariants, and those integer invariants are probably more related to Gromov invariants by a certain change of variables. So no one knows how to define Gromov invariants as far as directly, as far as I know. But you can simply take those linear combinations of Gromov invariants and then ask whether those are always integers. That's what integrality conjecture, which was proven recently by So there's another way, which basically says, takes the other perspective to have the second one on the curve. This new curve has Calabi Yau equations. How do you organize the equations in algebraic geometry? Well, it's using ideals. So you look at closed schemes of dimension most one. This is the modular creative, that's the Donaldson invariants. And the technical annoyance in this theory is C and how isolated. I use the letter C, but I suppose C sub dimension less than equal. So it can consist of some curves, with some embedded points, and some 3 points going. So this is the technical annoyance. And so Pandharipande and Thomas came up with an alternative, smaller compactification, whose definition is a little bit more complicated, but basically it consists of a coherent sheet on X of support one-dimensional, and a section of that sheet whose cokernel has zero-dimensional support. So you can get this cokernel sort of replacement for these 3 rubber points, but now it's past the lines. And in these theories, there's no automorphisms anymore, and so these are integer invariants. Although those are not the visual. Point out, so Donaldson, Thomas, and Pandharipande invariants. Well, they're not they're not literally the same numbers, but there's an equivalence of generated from them. Which is a very difficult result, but at least these compactifications are the same in nature. So, on the other hand, the Gromov compactification is very different, and it's not clear that you should expect any sort of relation between the resulting invariants. It's not clear to me, and there's no real, as far as I know, geometric relation between these two. And the other two. Okay, nevertheless, there's a conjecture, more like Microsoft open problem Pandharipande, which says that in fact there is a relation. So objective well, we got threefold X and multiply generating functions. So the rational growth invariants are rational numbers, and they're associated to threefold homology class, and I can also fix the arithmetic order characteristic. And so I record that as well. Once you fix the arithmetic order characteristic, then most of the pass together. Similarly, Thomas invariants are X multiple class, and now you can record, I guess, the whole order characteristic. That so these are related by changing variables Q equals minus V. Which is an interesting change of variables since these are formal expansions around U equals 0 and Q equals 0, but this change of variables since U equals 0, Q equals 1. So implicit is some sort of analytic continuation of the PT power series from Q equals 0 to Q equals 1. And in fact, that thing P should be a rational function of Q. Depending on certainty power. Yeah, if I was, if this were some statement about how, which if the change, sorry, the change of variable perspective of the point at which it's a formal expansion around, then it would amount to, a series of linear relations between finite coefficients here, finite coefficients here. But it's not of that form. It's these are expansions for every a priori false, all ensemble, all other Okay, so there are these compactifications. And now there's a great paper of Pandharipande called 6.5 ways of counting curves. So you see, I didn't cover all 6.5, and there are probably many more. So it's not like this is the only way of counting curves. So it's reasonable to ask, how do you organize all these theories together? And maybe the way it allows you to say something about this conjecture. There are many computations. I don't know, computations people confuse invariants in many cases. And all the computations point to basically saying that there's only one way to come. And any way you could come up with it, always give you something which, is equivalent to either of these, possibly by some kind of application. So that gets back to like top university conference. First, I want to describe how to do that using this very old and very polylogical idea of so currently it's where all of the mathematics is probably the first one. You've seen the effective on those X topological space. Then you can say, or the characteristic is I X sum really in group G with the property that I E equals I E prime prime for any short exact. So it's pretty easy to see that there's a universal. So and takes values in the paper. So we just take the really active on those and do the close effects. The double prime. And it's universal in the sense that any other characteristic. Hi. There's a C. Homomorphism take 0 x to G. Giving rise to that. So you can do this sort of construction. Many effects. Also do this. This is common. Case reviews. Right, so you can take can be established as counts. Okay. We really group on all say polygons in R2. Modulo. Well, you can code it by a few different things. So let's just say, let's just now pronounce it translation, rotation, and cutting. All right, so it turns out 0. Scissors congress group. Q is isomorphic to R, and the isomorphism is given by R. So you might ask, well, is there some exotic notion of area? So polygons not be some way of associating some elements including group to any polygon R2, which is the translation invariant, rotation invariant type. And this theorem says that there's nothing of well. Now we know from Hilbert's problem that scissors conference group in R3 is not just the area. And in fact, sorry, it's not just the volume. But in fact, what it is, it's the volume plus the data in there. That's it. too high, some of the edges, length of the edge, and I think beyond these two cases, these are mostly unknown. Maybe they're known you can put in sticks, but I'm pretty sure H3. No, maybe H3. It's definitely unknown for more complicated sticks. It gets into questions of homology groups, D groups, maybe discrete. Unknown outside small. And there's also Grothendieck group of algebraic varieties in zero varieties over C. Varieties of C modulo, then you say that X is equal to Z plus X minus C. And it's closed. So that's an interesting Greek theorem. Okay, so now I'm going to form Grothendieck group of one cycles in complex group. Now, the definition is going to have the same sort of follow-up. And what it will be is either the recipient of universal for enumeration. Invariant with what problem? Here, the problem is additive units for the exact sequences to find variant operations. Yeah, I'm gonna wait to do either one, but the harder one is the integrable done. So that's the one. Is definition. And then maybe I could also say with local on the again. Local on the base of one side. So B is the X is threefold. D of X is the space of compact one cycle on that. So one cycle is just formal linear combination of curves. These are non-negative integers and CI is reduced to reduce one. So they'll look like this X, cycle is like curves with some multiples. I mean, it's a topological space. The top of one cycle be nearby another cycle. And if I have a family, we generally have a family of threefolds. Then I can look at the relative set of things. The effects it would be is the space of pairs, point of base, and a cycle in that file. Space of cycles in something. compactification out of the way, make the homological definition. Ready? So, approximation. Take the direct sum over all threefolds of the economical compact support of the cycle. So, what is the economical compact support? It's just a freewheeling group on the compact connected components. So, I have so these multiplied spaces and bar C and bar DW. There are any curves in this actual multiple spaces. They all have an underlying one side. And these maps are proper ones to fix the lower right characters. You can push forward virtual cycles to get something we're on here. And so anytime there's a compact connected component here, we can count the curves in that connection. Count the curves the underlying cycle lies in that next component of the provided component. So any enumerative invariant has gives you a homework. So now I'll just qualify definition. So direct sum of all one parallel families of complex. So take your compact support of the relative cycle. You could take a cycle and do yeah, but the take connected tunnel, the intersection of zero. The co-kernel, I guess, this homology of the moduli space of complex threefold with coefficients in compactly supported forms. So this is what we might call this. This is a perfectly reasonable group in terms of vague definition, I believe. There. But it's not so great to actually use. There's not enough flexibility in complex people to actually use. The better definition would be to look at this complex and say, well, I shouldn't really stop at one parallel fact. Naturally looks like a certain gene complex which infinite in this direction and consider expanding threefold overall sympathy. And there's also no reason to stop at H0 complex before they get the power check. So that's really the group that we want to consider. I'll call that H and H1 complex support. C over so it's exactly what it's take all values of complex threefolds over simplicity fault matches of technical chains on space of relevant cycles. And differential what you expect. Or what you expect, some of them now, so this is right, so sorry. I mean this is the hot. This is a chain complex. So this also I call the Grothendieck group of one cycle. And you can sort of think of this as homology of moduli space of complex threefolds with coefficients in trivialized compact support total of great. Anytime you have a coherent virtual fundamental cycle on all of these bases of cycles on complex threefolds, which is something you get from this theory of relative impact. The other such theory, you get a homomorphism. So enumerative invariants of complex threefolds are really thought of homomorphism of the. Okay. And we might say, X beta, say projected threefold on multi-class, and X prime, beta prime, another threefold, another multi-class are numeratively equivalent when the same class. They represent the same class in this group, but any reasonable enumerative invariant is not going to be the same answer. Now, this definition is really motivated by Arthur work on TV conjecture. Read their paper carefully, and you see that really what they're showing, is that every symplectic Calabi Yau threefold is equivalent, enumeratively equivalent, as equivalent in an appropriate group of cycles to a linear combination of local curves. And the GV conjecture is known the local curves by. So really what they prove is something much stronger. They prove something not something about Gromov invariant to linear combination specifically, but really a very geometric statement about just not sure any enumerative invariants of symplectic block. Yeah, so getting back to this question about complex threefolds or almost complex threefolds. So this conjecture, the GD conjecture, that dealt only with Gromov invariants. And Gromov invariants, well, they're describable by this nonlinear elliptic setup, differential geometric setup. So they make sense in almost complex sense. And so, in their proof of the GD conjecture, he and Parker, they're really working with a Grothendieck group here, almost complex student. And that's a much more flexible setting. Now, if we want to be able to say something about Pandharipande Thompson invariants or Donaldson Thompson invariants, those, as far as we know, only exist in their own good definitions of those in the integral sense. That's never coherent sheet doesn't. You don't know that. But there are many more enumerative invariants in the integral sense. And that gives a group to which the part has gone to apply. So we need some more to say something more for that. Okay, so let's say here about this group, but first I want definition. So one cycle called Gromov when each of all of the curves pair non-negatively. So for example, if X is Calabi Yau, it's first chain class of 0. So the semicolon cycles form an oval. That's because in the negative, we give a cycle, all that happens is C out of together. And so you can form the Grothendieck group of semicolons. So this theorem it's really a transversality statement about unobstructedness, and it really requires this logic. I have no idea how to properly restore the false. This was semicolon. So this group is actually quite simple. So in virtual dimension equals 0, the three polynomials. Generates X, G, and K, genus, and multiplicity K is turn number. And the multiplicity should be 1 unless K equals 0. And it's 1 on K. And these are called elements. And the reason is that if I have a so-called local curve, that just means rank 2 vector bundle over curve. So that's a threefold. Those base is threefold. Then I can look at I can try to not cycles. Not all cycles, curve is local curve. That doesn't seem like such a great thing to do because those basic cycles, except in trivial cases, very non-compact because there's C star scaling action. But if you work equivariantly with respect to action, then the count curves all the way as a fixed locus to be done. Fixed locus just curves on the series. So that is these elements, X, G, and K, are elements of the Grothendieck group, which correspond to equivariant. Local curves are one of them. Maybe first examples, first geometric settings in Gromov invariants, Pandharipande invariants, Donaldson invariants are actually computed explicitly. And in particular, this MNOP conjectures have been known a long time with local curves. So the corollary is MNOP holds for X and beta with yeah, so for the next year, so I only stated MNOP in the Calabi Yau case. in case of no insertion. This formalism also allows you to treat the case so-called primary insertions, where you just go back, pull them off the past on M, on X, rather, and you grow up with theory of theory with those instance conditions. Now you can also write down MNOP conjecture for descendant insertions, but this doesn't help. Okay, so let me give some very brief indications of so as I said, this is generic. Oh, okay. Okay, and this explains the semicolon. Necessary. So in the almost complex setting, it's well known that a generic almost complex structure is what I like to call regular. In the sense that all simple curves, simple meaning they're not multiple colors, are unconjectured. Or generic, almost complex. Now, it's unclear what you even mean by generic complex. If I have a closed complex manifold, definitions of the complex structure of ground have a H1 anticanonical, and that might, for instance, that might just be zero. But even if it's not zero, it's most bidimensional space it will project it. Whereas for almost complex structure, you have local theory. And then you need that that wide variety of sufficient the abundance of high local deformations to get the same. That's really what's done. So for almost complex structures, and complex structures, will not be so generic complex structure on something closed and not so the generic complex structure on a neighborhood of a given one cycle are regular. So if I have a complex threefold X and the one cycle, yeah, and I then decide, well, I'm going to restrict attention just to this small neighborhood of the one cycle. Then what you can do is you can choose some transverse divisor E, and using a section of the tensor bubble, you find here D and as a pole on D to use the flow of that to reglue. For generic regluing, the one cycle will be good. So this allows you, in an almost complex setting, generic almost complex structure will give you regularity over the entire space of time. In a complex setting, you can get regularity only in a small neighborhood of the given point on the space. So it's a much weaker statement. And that is why you need this entire complex in that path. Almost complex. Because it allows you to consider bounds over height. Basics. However, higher spaces. That's like basically you want to take a perturbation of this space of cycles, where the perturbation you take perturbation target takes or depends on the cycle here. Now you're looking at the space of cycles to be very high. That's the first thing to do. Yeah, now the next thing you need is you need to have enough devices. So by a single curve, like there's a single one cycle, then well, it's pretty easy to see that you can always pick some local divisors, which puncture, all the theories for the curve. That's just a local control. But we need to be able to do this as balance. And that's much less clear because if I take just a generic approach of these divisors, the one parameter in a sufficiently high dimensional parameter family, those divisors will intersect. And that's not so good because I want to, each divisor choose a vector field to be blue and they're overlapping. So it's not trivial to get distant divisors. I'm going to say it for consider. So it's X over B family. Threefold. Three doesn't really matter. And we have compact analytic space of cycle towards the projection. Okay. D. Yeah. So basically for every point, maybe not for every point, but for some points in the base, I choose a cycle. Maybe I don't choose a cycle for every point, but for a given point, I choose both one cycle. I want to make that cycle contribute. So then, after replacing X with the neighborhood of support. Okay. Find point. Relative divided the I side X. Let's go over some over. That's space. Such that every the A is controlled by some this means every component of C intersects C. Oh, so as I said, if you just choose your divisors generically, you could prove this up to this issue of not being disclosed. Now, what you choose your divisors generically, but maybe they're not disclosed. So, but how that's going to be? So, let's see what was the intersection of the generically shows a divisor. Well, First of all, remember, we're allowed to cut out all but just the finite, small open neighborhoods. So really, if I have two divisors and they intersect like this, that's fine. I can just throw that one. It's outside my neighborhood. So let's see. So really, I only care about ensuring that the divisors are disjoint in as much as they intersect such. So really that amounts to, and those intersections are a bunch of points. You imagine you have a bunch of points on the one cycle moving around the family. The condition that two of those points coincide is called compactification. So if I choose divisors generically, I can solve this except over subset of K, which is compactification one. But then we use induction. So my induction dimension statement is true for that dimension one. Okay. And then away from that dimension one subset. So okay, so I think that's all.
The question is always. Thank you very much.